Hey there, guys and gals. What we're going to do today is look at a latent heat example problem. So think back to when we were doing specific heat type problems where we said, say we have a sample of liquid water that we're raising from a temperature of 20 degrees to 50 degrees Celsius. And we would use the specific heat equation, which if you'll recall, let me write this over here, our specific heat equation tells us that the heat is equal to the mass of our substance times the specific heat times the change in temperature. This is for cases where the temperature changes. During a phase change, we know that the temperature does not change, and so this equation is not any good for us if there's a phase change going on. So this one right here is for sorry, I lost that for a second. Not for use with phase changes. Let me just write that in there. This is not for use with phase changes. So this only works if we've got the same phase, solid, liquid, or gas, all the way through. If we have different phases, then we're going to have to use this equation, that the amount of energy is equal to the mass times the latent heat. And this is different for different changes in states, or phases rather. If you're going between solid and liquid, so that is either melting or freezing, either one, you use what's called the heat of fusion. So if you think about liquid water freezing, those atoms are kind of fusing together. So the latent heat of fusion is the energy that's used to either freeze or melt whatever substance you have. And here for water, it's different for every substance. So if this is a substance other than water, you're going to have to look up what the heat of fusion or heat of vaporization is. But for water, the heat of fusion is 334 joules per gram. That means for every 1 gram of water that you're either going to freeze or melt, the change in energy has to be 334 joules. Heat of vaporization is for the change between liquid and gas. So that's either vaporization or condensation. And for water, again, this is different for different substances. For water, the heat of vaporization is 2,260 joules per gram. And knowing this equation allows us to find energy changes when there's a change in temperature. This equation allows us to find energy changes during a phase change. So what we have to do in a situation like this is first determine at what points are we going to have a phase change and at what points are we going to have temperature changes. So we start with ice, and the first thing that happens, that ice is at negative 15 degrees Celsius. And we're going to warm that up until it melts, because we're heating it until it's steam. So we're going to warm that up until it's, wow, I can write this morning, until it is ice at 0 degrees Celsius. And we have to know the freezing and boiling points of the substance to know where the phase changes are going to happen. So again, if you don't know those, you'll have to look them up for the problem. For water, the melting point or freezing point, whichever way you want to think about it, is at 0 degrees Celsius. All right, from there, it was ice. Now it's going to change into liquid water at 0 degrees Celsius. So that right there is our phase change. And then the water is going to heat up all the way to 100 degrees Celsius. And this is just another change where the temperature is changing. It stays the same phase. And then that water is going to turn into steam or water vapor at 100 degrees Celsius. Again, no change in temperature. So what I'm going to do is I'm going to divide these up into separate problems because we do have to work them separately. And for each one, I can determine which equation it is that I'm going to use to calculate the change in energy there. So here we have ice that is heating up. That's a change in temperature So I can use this equation. Here I have ice changing to water. That's a phase change. So I'll need to use the latent heat. And in this case, I'm going from a solid to a liquid. So in particular, I'll use the heat of fusion. Here again, we have a temperature change. So that's just MC delta T. And here, I've got another phase change. And it has just occurred to me, well, before we jump into that, this is a phase change here between liquid and gas. So this would be the heat of vaporization. It occurs to me we need a mass of ice. Let's pick something easy. Well, let's say we have 10 grams of ice. Nice and simple that way. All right. Let's start here with our temperature change for the ice. We're interested in finding the energy, that is the heat that has to flow into this. We know the mass, because we had just labeled it. The mass of the ice, we have 10 grams of it. And now I need the specific heat of ice, not for water, but for ice. So I go and I look up what that is. If you aren't giving this in the problem, find it on the internet. The information's out there. You just have to go get it. So we need the specific heat of ice. So the specific heat of solid water is 2.1 joules per gram degrees Celsius. And my change in temperature, I'm going from negative 15 to 0. So my change in temperature is 15. And now all that's left is the calculator portion of this. And so all you have to do is type it in and see what results. So 21 times 15, 315. So the amount of energy required to heat up that ice was 315 joules. And again, if you're still not comfortable with about how much energy 1 joule is, your standard match is going to transfer about 1,000 joules of energy. So that gives you some idea of what we're talking about. So that's if you just strike a match and let it burn out. You'll get about 1,000 joules. All right, now we have ice changing into water. Well, we've still got 10 grams. The mass isn't going to change. And the heat of fusion of water now is 334. So to find the energy required to melt 10 grams of this, I just multiply those together, and that energy is going to be 3,340 joules. Don't even need a calculator for that one. Now we have our situation where water's heating up. So just as before, the mass is 10. We now need the specific heat of water, like liquid water, and that is 4.18. And our temperature change this time is 100. So the amount of energy required will be, unless I'm mistaken, there's 1, 2, 3, yes, 4,180 joules. Now our last one, water turning into steam, we need to know how much energy that is. We've got 10 grams of our water still. The mass isn't going anywhere. And the heat of vaporization, that is the amount of heat required to change it from a liquid to a gas, is 2,260 joules for every gram. We've got 10 grams, so we multiply those two, and it's 22,000 joules of energy. So you can see that almost all of the energy requirement here is coming from this last one. Now, our problem asks us to calculate the total energy required to do this, and in order to do that, all we have to do is add up all the energy for all the individual parts. And thank goodness for calculators, we can just put that right in. We find that the total amount of energy needed, we'll write this up here confusingly, so the total energy, total heat transfer in order to make this happen would be 30,435 joules. I'll put a box around that so that we know it's our answer. So again, what I have to do is divide the problem up into different sections. Areas where the temperature is changing and the phase is not, or areas where the phase is changing and consequently the temperature is not. and calculate the energy for those individually. Now also note that on these, there are a lot of curveballs I can throw at you, and I will throw a lot of curveballs at you. Maybe I will tell you the energy involved here and give you the total energy and make you find this energy. Something where I'm asking you to really use your brain on this. Make sure you understand this process, and then from there it's just using common sense and thought to see what all we can find from this. Good luck.